Hi, and welcome back. This is going to be a slightly different presentation today. What I'm going to be discussing are actual limits to human performance. Now, I know this is something that's been discussed in the Vanguard section, but what I want to talk about more here are what are the biological constraints to how strong a human can get, how fast a human can sprint, how fast a human can run a marathon. So I want to just delve into a little bit of the physiology kind of underlying these different challenges and maybe give you some sense of what humans would actually be capable of. So this is going to start out with discussions on strength. It's going to progress to sprinting, then to the marathon, and then to kind of unlimited slash ultra distance. So depending on what your area of interest is, you may want to skip ahead. So yes, what are we actually discussing? And again, as stated, the actual limiting factors in human speed, strength, and endurance. Now, if you look at human performance, especially over the last 100 years or so, when we've been tracking, Olympic records and the like, human performance is on an upward trajectory. Of course, we're, reaching asymptotes with, major milestones falling more and more slowly over time. You can see these kind of things in, sprint speed, 100-meter speed, mile speed, marathon speed. And occasionally you'll see little upticks in performance as technology improves and changes. But for the most part, we're really pushing the limits of human performance. Of course, when we talk about humans, we're talking about Homo sapiens. Even among humans and our ancestors, we are by far the furthest from the highest performers. I mean, for example, if you look at Neanderthals, they were significantly stronger. Estimates do say, as listed here, a typical 5'6" Neanderthal had the proportions and upper body strength to bench press 500 pounds. The average female Neanderthal could likely bench press the equivalent of about 350 pounds. So bear in mind, again, this is for a Neanderthal of average proportions. So you can already see that even among the Homo species, or the Homo genus, we are far from the most exceptional. So what we're talking about here are actual structural limitations to size, strength, leg speed, durability. So we're going to talk a little bit about muscle physiology, biomechanics, task specificity, nutrient absorption, and a few other things. First segment, could a human being ever deadlift a ton? Well, as we've seen, obviously that seems well outside the realm of possibility, given that, already when we look at 900-pound deadlifts, it's pretty rarefied air, and 1,000-pound deadlifts is extremely rare, and in fact, usually constrained to the use of special equipment, strongman style. You're talking straps, you're talking longer bars and the like, but still within the realm of possibility. So what we're talking about here are pure strength limitations, and strength limitations specifically in a 1-rep max. Now, one of the things we need to distinguish between is actual muscle contractile strength versus task strength. Now, contractile strength is the ability of a muscle fiber to actually do productive work when it contracts. If you look at a muscle, you take a muscle, say, outside of your body, and stimulate it maximally, what is the actual strength by which it contracts? That's limited by fiber type, coordination, again, neural coordination, the ability of all motor units to fire at once, and chiefly the cross-sectional area of the muscle. Now, task strength, as we're discussing it here, is the ability of the muscle to coordinate with others across joints to carry out specific work. In other words, the ability to actually, say, do a squat rather than just have a leg muscle contract. So we're going to discuss the biological limitations of both to determine how realistic, and the practical limitations to determine how realistic this is. So first, muscle contraction. It is, as you see, in part dictated by the coordination of muscle fibers and the rate at which they are recruited. Now, this is very, very relevant. Of course, we know that as you train more and more, muscle twitch, muscle contraction becomes a more coordinated movement. If you're not familiar with the concept, which I assume most of you are, but if you're not, think about two teams playing tug of war. One team just decides, they're going to have their people just kind of pull whenever they want, or, they say go and they all slowly grab a hold and start pulling on the rope. And the other side all says go at once and they all pull at the exact same time. The side that pulls at the exact same time is easily going to drag the other ones into the mud. This kind of coordination, is really, it's just training. The more you train, the more you practice a movement, the more coordinated your muscle fibers are, and the faster you kind of recruit every available motor unit in the motor pool. Now, second type of contractive modification is fiber type modifications. We talk about fast twitch, slow twitch. We can talk about MHC, heavy, light, type 1, type 2 chains, all that kind of nonsense. But if you think about it, most people are familiar with the idea of fast twitch muscles, which are generally the kind of motor units, muscle fibers and motor units that are very powerful in terms of their contractile strength, contract very quickly, but are not, or they're easily fatigued, versus the more slow twitch, which are more fatigue resistant, but are recruited more slowly and don't necessarily generate as much force per contraction or contribute as much. One thing that's interesting to note, though, there are a lot of discussions about how strong certain other apes are. We look at chimpanzees, we look at gorillas, and one of the theories is that the muscle fiber type is dramatically different in these animals. The answer to that, the real reality there, is that they're actually not. For example, chimpanzees, which are notoriously strong and famous for being much stronger than humans for their size, they really only have about 3% more fast twitch muscle in the typical muscle group than humans do. So there's not a major difference here. So it's pretty clear that even within primates, muscle fiber type, even though there's some individual potential for fiber type shift, this is not a major factor, and it's unlikely that evolutionarily we're going to get any major shifts across generation after generation. So, fiber type can change via training, but the changes are not immutable, and again, still relatively minor in the scheme of things. Now, the actual contractile force of the muscle is, of course, also going to be heavily dictated by the number of muscle fibers that are actually contracting at once. You'll absolutely have an upper limit based on cross-sectional area. This obviously makes sense. At the end of the day, you've got your actin and myosin. They're contracting. The more of those you have, the stronger a muscle is going to be. Of course, the cross-sectional area has an upper limit. So the question here is hypertrophy potential unlimited. I mean, if you think about a human being being able to deadlift a ton, well, what if you had a human being who was 500 pounds of solid muscle? Then surely this individual would be significantly stronger. So is that even possible? Well, okay. Just backing up for 1 second. Now, when you look at muscle contractile force, remember, this is just a quick diagram of contracting muscles here. You can see the thick filaments, the thin filaments, the actin and myosin. You can see the little heads on the myosin that pull across the actin. And you can see that those actin filaments are gradually pulled together. Now, when a muscle is fully stretched, you see in the top diagram there, a lot of those myosin heads are not actually touching any actin. That is why when a muscle is fully stretched, it is not capable of generating as much contractile force than when it is contracted. In the middle position there, partially contracted muscle, you see all those myosin heads are actually touching actin. At that point, the muscle has the greatest ability to contract and produce actual force. If you look at the bottom diagram now, note that some of the actin is actually overlapping at this point when it's fully contracted. At that point, the myosin is no longer able to bind to as many sites as in a partially contracted muscle. So there is a sweet spot for human muscle contractile strength. When it's fully stretched or fully contracted, it does not contract as hard. This is important to note when it comes to task work. Because contractile force, again, is not linear. You have that sweet spot of maximum work. So for a task to be completed, to lift a bar, to deadlift a weight, to squat a weight, overall muscle strength, and that means all the muscles involved, needs to be sufficient to overcome cumulative load at all points. Extremes of range of motion, bottom of a squat, for example, or sticking points, that position right below parallel in squats, are usually a combination of less favorable muscle lengths or less favorable lever arms. Now, it can be both in many cases, and a lot of this depends on individual biomechanics. Now, this is why changing stances works for some people. Because what you're doing, say when you widen a squat, you could be putting certain muscles in more favorable leverages based on your femur length, based on your muscle attachment points, or whatever else. You may actually be putting, whereas what was before a mechanical sticking point as far as lever arms, you may be stretching or contracting certain muscles to the point where they are actually able to generate more force through that sticking point, thus potentially making that not a sticking point anymore, or allowing you to do more task work with the same amount of individual muscle contractile work. That is important to note as well, because this is, quite frankly, why some individuals, yes, there are a lot of factors involved, but this is why some individuals are better sumo deadlifters, some are better conventional. Yes, there's always the question of lever arms, but there's also, again, question of attachment points and position where each engaged muscle is the strongest. So what we need is, again, at those positions, we need the greatest muscular force to be either at that sticking point or prior to that sticking point. In fact, prior to that sticking point is fairly significant. You can generate enough force out of the bottom of a movement to propel load through sticking points. Witness lifters who bounce at the bottom of a squat, and what they're doing is they're using a lot of, say, even glute force and the like to be able to propel them up through that point where they would stick at if they had to stop. You can also see the same with the bench press. If you've ever done paused benches or spinal press or anything like that, you may notice the difference. Now, coordination also needs to be developed. Remember, we're talking about 1 repetition max strength here. Now, maximum force generated in a single repetition rarely includes your full motor pool of fibers. In fact, it is very challenging for this to do so. It may take multiple repetitions to actually begin engaging all the relevant muscle groups. If you can, in fact, exhaust pretty much every single muscle fiber and motor unit in a single repetition, that's all you would need, for example, to elicit hypertrophy, but that is not the case. As you, of course, get more and more coordinated, the proportion of motor units engaged in a single repetition can increase, but it's never going to be all of them. So, all right, so that's a little bit just on proportions and the like. But could a human being ever deadlift? Let's talk about hypertrophy. Okay, so how about this theoretical 500-pound human? So a bigger muscle, yes, is a stronger muscle, except when it isn't. So yes, muscle size is limited by, and we're going to go through the list, myostatin. A lot of folks are familiar with myostatin. They became popular a while ago. People were talking about myostatin inhibitors. People talk about myostatin knockouts. Certain species of cow or certain types of cows, for example, that what is it, the Belgian blue or something like that, or is that a type of cheese? I'm not sure. But either way, the cow that has a huge amount of musculature tends to have some sort of either myostatin deletion or flaw in the gene that allows for unlimited muscle growth or nearly unlimited muscle growth. There's also theory that several professional bodybuilders also have either one copy of the gene or just defective copies of the genes, which allows them to put on a lot more muscle. Now, there is a downside, of course, to no myostatin whatsoever. No myostatin would be very dangerous for your heart, for example, because myostatin is responsible for also restricting the amount of cardiac growth and the like. So we don't want to knock that out entirely. But still, it is a limiting factor. Now, androgen levels are also, of course, a limiting factor, and we know that use of anabolic androgenic steroids can make a difference here. The androgen receptor, there are various androgen receptor-mediated pathways that allow for muscle size and strength, and of course, muscle maintenance, nutrient partitioning, and the like. Again, nutrient state surplus. Obviously you need to feed skeletal muscle. You need to ensure a steady supply of both glycogen and, of course, amino acids, preventing cannibalization and ensuring that there is sufficient amino acids to actually be incorporated into muscle tissue. And, of course, perfusion. There needs to be enough nutrients getting to the muscle, enough vasculature to keep the muscles alive and allow them to do work. So those are some limits. Now, we also have mechanical limits, and this is where it gets a little bit stickier, and I think this is something that really needs a lot more discussion. So, we talked about the tendon and the thesis cross-sectional area. That is static. Now, the latter word there refers to the area in which the tendon actually attaches to the bone. Now, tendons can, of course, adapt. You can get a certain amount of tendon reformation and strengthening, and certainly the attachment points to the bone. The bone in that area can get more robust with loading. You get those osteocytes that detect the additional load, and not only do they strengthen the bone, but they also strengthen those attachment points and make them more robust. But the cross-sectional area is largely fixed. Now, usually that is not a problem. Oh, also the size of the aponeuroses, which are kind of the flat fibrous tendon-like segments that you'll see in certain muscles, like say the mid part of the tricep or certain parts of the abdominals, etc. Now, when of course if those are largely fixed, and you say, well, are they going to rupture? Are they going to be damaged? The answer to that is no. Tendons typically have far more strength than muscles could ever practically generate. When tendons are usually torn, it's usually because of trauma or some sort of torsion or chronic inflammation that leads to existing structural weaknesses. But a healthy tendon, it is extremely, extremely unlikely that a muscle will ever rupture a tendon. It is far more likely that muscle fibers themselves, as a muscle gets bigger, the tendon is no longer the weak point. The muscle fibers themselves will be the weak point. So basically the muscle it's much softer and squishier. Remember, that's also absorbing the load. If a very, very large muscle theoretically generates too much force, it's not going to rupture the tendon. It's going to rupture itself, again, unless there's some sort of pre-existing injury. So, practically speaking, though, what is the limit of this attachment size? Well, it means that if you're trying to add on more muscle fibers, you're going to have to somehow put them somewhere, right? Now, we're going to see on the next slide, and we can even pop over to that in a moment, but the pennation angle, we're all familiar with, you talk about both parallel, fusiform, and pennate muscles. we're talking about how the muscle fibers are aligned. Most folks are familiar with the diagrams you see of, say, the rectus femoris or the deltoids, the medial deltoid. The muscles kind of arrange themselves in almost a fan type shape. That's pennation. Now, when you add on more muscle fibers in a pennated muscle, what you're actually doing in many cases is to increase the number of fibers, you're going to increase the pennation angle. If you think about only having a few muscle fibers, that pennation angle will be almost parallel to the angle of pull. Now, as you add on more fibers, that pennation angle is going to slowly increase with all those fibers slowly fanning out more and more and more. The problem with that is when you get past about 45 degrees and you keep adding them on, actual muscle production decreases. The discrete contribution of each contraction to muscle movement goes down. I mean, think about it. If the fibers were to just keep growing and growing and growing and pennate out to a 60 or 70 or 80 degree angle, extra contraction wouldn't really be doing much practical work. So that becomes an issue. Well, how about a flat muscle like a parallel muscle or a fusiform muscle? Well, the other issue there is when you start adding on more and more muscle fibers, eventually the muscle starts to curve. Think about a very large bicep muscle when it contracts and how it bulges out. So the problem with that is twofold. First of all, as new fibers get deposited, and you think about them just, for example, depositing on the outside, what's going to start happening is they're going to start creating their own pennation angle. In other words, if you were to start bowing this out, almost like inflating a balloon, if you think about those muscle fibers on the outside, they're not necessarily pulling straight with the angle of pull, are they? They're going to be pulling at a side, at angles from the side. So every successive muscle fiber that you add that increases that cross-sectional area is doing proportionately less direct work. The other issue is that as those muscle fibers layer on and the muscle gets wider, those outer fibers, when they contract, are effectively compressing the inner fibers. Now, when a fiber contracts, it also expands. It also bulges, again, as those protein chains go over each other and you start to get vascular occlusion and the like. If a muscle gets too big, those outer fibers contracting are going to inhibit the inner fibers' ability to contract. So those muscles, as they get bigger and bigger and bigger, get significantly less efficient. And eventually you reach a point where not only are these new muscle fibers not producing any extra work, they are limiting the work of the existing fibers. And of course, they're limiting the practical range of motion. So here we just have a quick diagram. If you look at the fusiform muscle especially, you can see already the muscle fibers on the outside, how they create a pennation angle. If you look at the bipennate muscle there, again, think about what would happen as those start to form up and start to bulge out, especially the ones at the top there. So that's kind of what I was referring to. Now, in spite of that, we also have limitations to hypertrophy. Now, yes, these are obviously problems we've been discussing when a muscle gets very large, but what about at a slightly smaller level? Well, yes, there are limits to our ability to grow muscle from a biological and practical standpoint. So, the more hypertrophied a muscle is, the harder it is to stimulate, again, both tension-wise and mechanically. If you think about it, yes, you're going to have to keep lifting more and more weight. You're going to have to be moving greater and greater loads. There's going to be certain structures, again, bone, connective tissue, things like that, that are going to get stressed more and more and more, and maybe slower to adapt. You're also dealing with, again, certain fixed nutrient capacity, etc. So as the stimulus needed becomes greater and greater, the overall body becomes more and more taxed and has less ability. For example, the heart, GI tract, again, nutrient absorption and the like. A lot of these other systems that are not growing linearly with muscle size are being taxed more and more. Now, one thing to note here. I've actually had a few questions about this. Range of motion in a given task is more or less irrelevant. One of the things we were talking about is, of course, is sufficient hypertrophy or excessive hypertrophy going to limit your range of motion? For example, if a bicep gets very large, it makes it harder to do a full curl. If your hamstrings get very large, it's impossible to do a full depth squat. That doesn't really matter. Range of motion is more or less irrelevant. If you are contracting a muscle within its, kind of sweet spot of contraction, you are eliciting maximum tension. At full extension and full contraction, a muscle is not doing much practical work, and stimulation there is not needed to exhaust the full motor pool or all the different motor pools and actually achieve maximum stimulation. When you look at a specific task, like let's look at a squat, for example, A full depth squat is not necessary for hypertrophy of the legs. And the reason for that is, of course, if you look at a squat, as you go deeper, for example, certain muscle groups, yes, are activated preferentially at the bottom of a squat. If you want to use a squat for glute hypertrophy, the bottom of a squat is, of course, a great way to do it. But of course, there are other ways to stimulate the glutes that don't involve squatting. When you go down deeper in a squat, when you reach a certain point, certain biarticulate muscles, or muscles that cross more than one joint, for example, let's look at both the rectus femoris and a lot of the biceps femoris, both of those actually at the bottom of a squat are shortening as the hip angle changes and as the knee angle changes. In other words, when you go into more hip flexion, you also go into more knee flexion, and the muscle is not actually doing much practical additional work at that point. So basically, don't really worry about that limitation to range of motion when it comes to hypertrophy. Range of motion is far more important from an individual muscular standpoint and not from a gross movement standpoint. Really, the best movements for hypertrophy anyway are, in fact, majority of the time, more what would be considered isolations because they allow the target muscles to be the ones fatiguing, and you are not constraining the actual tension you can elicit from multiple muscles because of some limiting factor. So there you go. In other words, don't worry if you don't squat to death. Just make sure you work your glutes some other way. Anyway, that being said, larger muscles, again, slowly start to lose contractile strength due to mechanical factors mentioned. So the ability to actually generate maximum force with each muscle and actually achieve full contraction and exhaustion slowly begins to diminish. And of course, a nutrient and hormonal state becomes limiting. So yes, it's clear that human potential to hypertrophy is severely limited, even with unlimited drugs and myostatin knockouts and everything else. There's simple other metabolic and mechanical issues that would pretty much represent the human limit. It's pretty safe to say as well that there are actually some bodybuilders out there right now who are pretty much approaching that practical human limitation. So we also have those limitations to mechanical advantage and coordination. Fiber type is still limited. Coordination is not infinite, and ideal proportions for a deadlift may be practically impossible. Again, we talk about attachment points. We talk about ranges of motion and the like. We have tiny lifters who only have to move a bar through a very short range of motion, and that's because they are really only using their muscles at the position of maximum contraction. They're not necessarily stronger than other human beings their size, really. They are just capable of exerting better force, given their anthropometrics. In other words, the limitations here are going to be heavily because of just the human body shape. So, could somebody with Lamar Gant's proportions who is 500 pounds of solid muscle potentially deadlift 2,000 pounds or 2,500 pounds? Probably not. It's likely that human performance in this arena is already approaching a limit. We may see certain outliers based on, say, certain genetic conditions that may allow for significant improvements and significant performance. Especially in something that is relatively niche as powerlifting, we're seeing a lot of individuals migrating to the sport who are obscenely strong. But this just seems to be way too far outside of what is capable as individuals get bigger and stronger. Moving on. Could a human being ever sprint at 50 miles an hour? So this is interesting. So when we talk about sprints and we talk about running faster, people think, of course, about leg turnover, et cetera, et cetera. And we also think about sprinters needing to be strong. We think about them needing to be muscular. Well, the limiting factor in sprint speed is not strength. In fact, many sprinters are, significantly, in fact, stronger than they need to be. As it says, greater strength is associated with greater speed, but only to a point. There is not a linear correlation. If you look at a lot of sprinters, they are capable of producing a significantly more gross strength in both a squat and a, say, one-legged bound than they ever do in a sprint. I was reading one of the absolute worst books on strength training for runners I have ever read in my entire life. We won't get into the title, but it was basically a program to give sprinters greater and greater leg strength. That is not absolutely necessary. In fact, much past a certain point, if lifting speed slows down, and you get significant hypertrophy in the lower limbs, you will worsen your performance as a sprinter, and we'll get into that in a moment. What is really important is just rate of force development or rate of force generation, and we'll get into why in just a moment. But yes, typically speaking, if a stronger muscle will be able to generate a given percentage of its force and therefore generate more force over the same period of time, but that doesn't necessarily mean making a muscle stronger is necessarily the answer. There are also limiting factors to sprint speed, talk about swing time, gait mechanics, et cetera, but we're primarily going to talk about what the single biggest limitation is. Ground contact time. So, ground contact time is the amount of time that your foot is actually in contact with the ground, obviously. As your speed increases, of course, that ground contact time is going to decrease. What that means is fairly clear. As your foot touches the ground, it already begins to generate force. Now, if it lands directly under you, as soon as it hits the ground, it absorbs to a point of maximum contraction, and it starts generating a propulsive force forward. As ground contact time decreases, the total force overall decreases as well. So here is the problem. As you sprint faster and faster and faster, as a human starts to move faster and faster, that ground contact time is no longer sufficient to generate enough force to keep you moving forward. If you look at a lot of very, very fast animals, they have evolved to maximize their ground contact time. A cheetah's spine flexes like that not just to increase its stride length, but if you look at its particular gait, if you look at the picture on the left, notice how far forward those hind legs are coming and how far back those front legs are going. That is so that those hind legs hit the ground as far forward as possible so that when the cheetah hits the ground, you notice its spine is in full flexion there, when the cheetah hits the ground, it has all that time from that forward leg position all the way to that full extension with that bent back to generate force. That is why the spine flexes so much like that. And you can see that full extension, it's not because it's springing up. It's not necessarily because it's taking long strides because it needs to take long strides. It's doing that for the sole purpose of maximizing the amount of time for those back legs and front legs to generate force. Humans don't have that option, really. We don't have the ability to engage in any sort of galloping gait. Our pelvis shape is largely fixed. So what can we do to actually increase our ground contact time? Well, we can certainly improve rate of force production through training, explosive training, plyometric training, ballistic training. Yes, maximum strength training, but only to a certain point, and we'll get into why that's not a good idea for a while in a moment. We can also increase lower limb length. That could increase the ground contact time. However, if we increase lower limb length, we also make the limbs heavier, which can be a detriment. So it would be ideal to increase your lower limb length without increasing muscle mass but maintaining strength. This is why heavy strength training for sprinters may not be a great idea either. Because as that lower limb, that's why, getting ahead, that's why an individual like Usain Bolt is seen as kind of a bit of an aberration in this regard. Notice his long, skinny legs. Yes, he skinny relative to other sprinters. His lower limb length is actually allowing him a longer, greater ground contact time, but his legs may possibly weigh about the same as a lot of other sprinters. This is actually an advantage for him. Now, humans cannot gallop, but we can improve our economy. We'll get into that again in a moment. But also, yes, prosthetics. If we could increase lower limb length but decrease or eliminate weight, then that would be a huge advantage. When we talk about individuals like the infamous Oscar Pistorius, he was very slow to accelerate. If you look at a lot of Paralympic athletes, their hundreds are not that fast, relatively speaking, but their 400s become extremely fast. The amount of force that they generate early on is relatively low, but that very light limb, together with an increased ground contact time, allows them to generate significant amounts of force, but also to do this with a relatively low body weight in the limbs. So, if you take all of that together and you say, well, we can't increase muscle mass either, so heavy lifting is probably a bad idea, we get into this whole, what with normal human proportions, what would be possible based on maximum rate of force production as speed increases? Well, most models are showing that a top speed of about 33 miles an hour or 53 kilometers an hour is about the limit of what is possible under those parameters. Usain Bolt at maximum speed, which comes, I believe, about 60 to 70 meters into the sprint, can hit about 27 miles per hour. So human performance can still increase beyond what we're seeing here, and certainly speed extension means that our sprint times could still come down, but again, this is a theoretical human max. Another thing, no, cheetahs don't overheat, so please forget that. That's not going to be a limiting factor in proportion. We can also reduce upper body mass, mind you, but body mass needs to be maintained because you need sufficient strength and mass to counter the pelvic rotation of the lower limbs. So that is one other issue. Could a human being ever sprint at 50 miles an hour? Likely not. Anything beyond 33 would require proportions outside of those observed in humans, or rate of force production, which we can't achieve. Okay, so that's sprint speed. Now, could a human being ever run a sub 2 hour, let's say 150 marathon? So, what we're going to get into now is a little bit more granular with regards to actual aerobic endurance and physiological limits of aerobic endurance. So, what we're talking about here is we're talking about more factors like VO2 max, lactate threshold, etc. So, now, actual aerobic capacity as we measure VO2 max isn't necessarily the same thing as time trial performance. VO2 max is typically measured by kind of a step up test that relies on a lot of things, including motivation, but it also is not necessarily a test of endurance. In other words, we are not exhausting energy substrates to hit a VO2 max. VO2 max itself is a whole combination of indicators. It is basically the body's ability to utilize oxygen, as much oxygen as possible. Now, this is dependent on a number of factors. It includes circulation, it includes, the mitochondrial ability to actually utilize oxygen, etc. So it in and of itself is not a single variable factor. What limits our VO2 max? Technically saying, now, if you look at marathon performance and the fact that a higher VO2 max is typically associated with better marathons and better speed overall, is VO2 max the limiting factor here? I mean, what is it? Is how do we improve our VO2 max, or practically speaking, what is limiting human VO2 max? Well, in testing, it is actually a supply side issue. Full body mitochondrial capacity is limited by oxygen delivery, not by the number of mitochondria itself. In other words, improving circulation, improving the oxygen carrying capacity of the blood, improving stroke volume, etc., would do more to improve the average individual's VO2 max than any change on the cellular level. In other words, for most trained runners, if you could suddenly double the number of mitochondria in your cells, you would not notice a change in your VO2 max. However, that only means so much. Exhibited performance also involves the demand side, however. As duration increases, clearance of metabolites and ability to oxidize more fat becomes a determining factor. In other words, that's when the mitochondria come into play, not in a short-term VO2 max test, but moving more into the sort of lactate threshold and ability to maintain a percentage of your VO2 max. Now, bear in mind, when we talk about marathoners, yes, a great VO2 max is fantastic at all, but an individual who can maintain a higher percentage of a lower VO2 max may be capable of generating more power and may have better performance over time than an individual with a higher VO2 max that can only maintain a lower percentage of that over time. So, VO2 max itself can't really be seen. In other words, if we were going to predict human capacity here, simply going by VO2 max is not enough. In other words, if we could develop a human training protocol that is strictly based around increasing supply side, we're talking about anything from blood doping to cardiac hypertrophy and increasing capillary perfusion and et cetera, and even increasing the oxygen dissociation constant, the amount of oxygen released by the blood, that would not necessarily improve VO2 max. However, that might very well improve the exhibited VO2 max. Anyway, capillary density as well seems to be directly proportional to respiratory capacity of the muscle, more so than fiber type. Now that's significant. If we had an individual who was all type 1 fibers but had low capillary density, that individual would not necessarily perform any better. Yes, endurance athletes tend to have more type 1 fibers, but the individual fiber type itself does not seem to constrain the respiratory capacity of a muscle, which is interesting. Final point. Some folks have wondered about the central governor, if eliminating the central governor would allow for better human performance. The central governor model was proposed by Noakes based on earlier theories that were proposed as early as the 20s and 30s, but it doesn't appear to be a valid factor. First of all, mood or external motivators can override this system. In other words, an individual who appears to be pushing up at the limit of the central governor can actually have this overridden by something as simple as a smiling face or clapping crowd. That would already seem to say, well, this is not a very good central governor if all it takes is somebody smiling at you to override it. It is also not testable, falsifiable, or consistent. And of course, if a theory cannot be realistically falsified, it's probably not a very good theory. It's also not predictive of performance. In other words, it is a beautiful idea trying to say that there is an internal limiting factor that prevents us from hurting ourselves, but it doesn't appear to be valid. Anyway, that's an aside. So, VO2 max itself, there are theoretical limits. Growth in the last 100 years, yes, but there's certain outlier numbers that are suspect. There's for example, the individuals who are cross country skiers who have numbers that have been tested in the 90s, in theory that it's over 100. Those numbers tend to be pretty suspect. They haven't been validated or really repeated. But it's pretty clear that human values greater than 90, if they are ever achieved, are probably extraordinarily rare. Of course, that alone doesn't matter. Substrate utilization and mitochondrial density and ability to use fat for fuel matters, but so it seems would then glycogen storage. Bigger legs mean glycogen storage, and actually leg size as a percentage of runner size is positively correlated with better performance. But remember, that is a proportion of runner size. So any of you big folks out there thinking, hey, I've got these crazy big thighs, I'm sure they store a lot of glycogen. That's only really an advantage when we're talking about the difference between 232-pound Kenyans and one has legs that are 2% larger than the other at the same body weight, same height, and everything else. So there's definitely a sweet spot here. So analysis of times, an analysis of the times, putting a kind of an asymptote on it, puts the limit around 2 hours. But that, of course, does not account for unlimited adjuncts. In other words, unlimited blood doping. If we could, allow for unlimited blood doping, we could certainly increase the oxygen carrying capacity of the blood. But there's still, chances are, we've reached or come close to that upper limit in cycling with compounds like ITPP, which increases the dissociation constant, EPO, which increases the oxygen carrying capacity of the blood, etc. Those have all been pushed to near their limits in pro cycling, for example, and we still have not seen VO2 max numbers that exceed theoretical human, that exceed this, high 80s, low 90s. There are also dangers associated with the increase. Really, the increasing the hematocrit and continuously can actually lead to blood thickening, which can actually kill an individual. So anything that could seem to increase the VO2 max significantly more would probably kill you. So what we're left with is really improving performance at a percentage of VO2 max. But even that already, we're pushing the limits with certain marathoners able to maintain 88 to 90% of their VO2 max for the entire duration. The theoretical limit, therefore, would be an individual who could maintain 100% of their VO2 max for the full duration, but that in and of itself is a fairly hard asymptote. Other thoughts, we could improve the oxygen dissociation constant, but of course if that's too high, you have a poor quality of life. There are people who talk about the Bohr effect. Oh, what if we can tolerate more acidity at the muscles? Acidity in the muscles is not associated with inferior performance, so let's have our muscles get as acid as possible so we can tolerate higher amounts of lactate, etc. No, increased acidity at the muscles eventually leads to changes in blood pH overall, and a decrease in blood pH is associated with greater perception of fatigue, harder efforts, and eventually decreased systemic performance. So that is not an option. So could a human being ever run a 150 marathon? Well, it's pretty clear that with existing technology and improvements in technology, we can always push the limits a little further with a sub 2 hour marathon with, pacers and, we're talking about improved shoes, flat course, drafting and all that seems to be possible. But it's likely that we are already near the upper limit of VO2 max, at least under normal physiological conditions, even with blood doping and the like. So performance at percentage of VO2 max, we are again pushing the limits there. Regression models at this point would show that even with current technology, anything much faster than a 156 or 157 is likely impossible. Final segment, could a human being theoretically run forever? Well, the answer to that is yes. There is a single limiting factor to your daily output, and that is what is known as the alimentary limit, which I've discussed before. This is the maximum amount of nutrients that your body can absorb per day, which is typically about 2.5 times your basal metabolic rate. Now, bear in mind, this is subject to fluctuation. Extremely large individuals may have a high basal metabolic rate, but that doesn't necessarily mean they have more nutrient absorbing capacity. So it's more or less within the normal range of BMIs that you need to utilize this for. This is constrained, again, size of your GI tract and surface area for absorption. If the output is higher per day than 2.5 times your basal metabolic rate, your body starts to break down. It starts to break down muscle proteins. It starts to run into issues with essential fats. It may break down bone tissue. And eventually it just goes generally catabolic. Now, this can certainly take place for days and days, if not months. But The individual will undoubtedly be in an unsustainable situation as long as as long as their output is greater than 2.5 times their BMR. Also, bear in mind, injury, illness, other things also kind of cut into that a little bit. You get a cut on your foot or you start to get bruising or anything else. A lot of those are going to require additional energy to recover from. Glycogen or fat ratio of expenditure doesn't matter at this point. Alimentary limit is literally the only physiological parameter, again, provided individual stays healthy, that matters. This means that it doesn't matter what gender you are. It doesn't matter, what your fiber type composition is or anything else. It is simply as far as you can move with that level of output. And that is it. A human being could run forever, provided they stay within the output dictated by their alimentary limit, which is indeed fairly significant. I mean, if you look at an individual like, say, myself with a basal metabolic rate of about 2,300 calories per day, my general output could be the equivalent of well over a marathon per day on a flat surface, and I could technically keep doing that forever. Of course, that couldn't always be at a sprint, and after a day and a half, I'd probably have every orthopedic injury known to man, but nevertheless, that is a theoretical limit. So that is a quick rundown on what I would consider human performance limitations. I hope this was interesting, and thank you for listening.